Now we want to look at calculating the entropy change for the surroundings in a chemical reaction. So we've already looked at how to calculate delta S for the reaction. How did the entropy of those actual molecules change? We need to also get the delta S of the surroundings. How does our chemical reaction affect everything around it? Combining those will give us delta S of the universe, and the sign of that is going to tell us whether or not it's a spontaneous reaction. All right, so if we want to think about the surroundings, so our system is, our chemical reaction, and so this is going to be affecting the surroundings. And there are two primary methods for a chemical reaction to affect its surroundings, or really for any system to affect its surroundings. They're heat and work. Okay, you can either just have heat flowing out into a system, or the reaction could do work. It could expand, it could move the gas around it. So work, it's really just kind of moving things, right? It is directed motion. If a chemical reaction does work on its surroundings, that doesn't really change the entropy of the surroundings. If there is some gas, or say you form a bunch of gas and there's bubbles forming, they're just, say, moving water away, but they're not really changing the entropy of the solvent that you're in. Heat, on the other hand, if heat flows in or out of a chemical reaction, it will change the temperature of the surroundings. Say you're doing a chemical reaction in, say, water, that solvent will get hotter or colder, and that will affect the entropy of that water. So heat is the primary way that a chemical reaction affects the entropy of the surroundings. So exothermic reactions release heat. So that would be when delta H of the reaction is negative. So if an exothermic reaction releases heat, that causes a warming up of the surroundings. And so the entropy of the surroundings will increase, right? The molecules in this propane burn are becoming more, it is increasing the disorder because there's more molecules, there's more gas molecules that we've seen. But also the air over on we need a new color. The air over here is also being warmed up by the flame. And so these molecules start to move more, right? There's literally more motion in all of these molecules around this, increasing the disorder of this air, right? Making that motion go more, increasing that disorder. For an endothermic reaction, the opposite happens, right? Delta H would be positive and heat comes in from the surroundings, so we cool them off. So these ice cubes are melting. The ice cubes are melting, and the literal molecules in the ice are becoming more disordered because they're becoming liquid. But this water that's in the cup is getting colder. And because it's getting colder, there is less motion in those molecules, and the entropy of that surroundings is decreasing. So these relationships are always true. Exothermic reactions cause an increase in the entropy of the surroundings, whereas endothermic reactions cause a decrease in the entropy of the surroundings. So exothermic reactions, we've kind of talked about early on, we're talking about, kind of predictability, spontaneity. Exothermic reactions tend to happen because you're releasing energy from the reactants. The products are lower in energy, and that energy is being released as heat. So this is kind of a very common understanding as to why exothermic reactions, exothermicity is a tendency to occur. And we can change our perspective on that same exact idea in that exothermic reactions, the reason why they tend to happen, as we say, is because heat flowing into the surroundings increases the disorder of the surroundings. Doesn't matter how you slice it, it always has to come down to entropy. And the reason why is that you kind of spread out that energy. Instead of the energy being trapped in, say, the chemical bonds of the reactants, it's spread out as heat in the surroundings. And that sort of spreading out is an increase in entropy, an increasing in disorder. And so it's more common and more useful to think about, say, the energy of the molecules in your chemical reaction. But the real physics, we want to go hardcore physics reason, is that entropy of the surroundings is increasing. And really everything, whenever you're increasing entropy, that's always a tendency towards spontaneity. It's important to note, endothermic reactions happen, and the opposite is true for the entropy of the surroundings for endothermic processes. You can decrease the entropy of the surroundings. It just has to be compensated for by the change in entropy of the actual chemical reaction. So I want the entropy of the surroundings, and it's all based around the heat that's flowing into the surroundings. So in general, change in entropy due to heating is equal to the heat divided by the temperature at which it occurs. So this is the actual equation. This equation is generally true for changes in entropy based around heating. One of the things that comes from this equation is that at higher temperatures, so as T gets bigger, that's in the denominator of this fraction, and that the effective heat will decrease. So this equation contains the sort of the mathematics of the physics we described before, that it's hard to make something disordered when you're already at a really high temperature. So we want to make this a useful equation, though. This is generally true. How can we turn it into be useful? Well, the first thing we want to do is relate it to the reaction itself. And the heat flowing, basically the heat flow of a chemical reaction is perfectly opposite of the heat flowing into the surroundings. The Q of the surroundings is the negative of the heat of the reaction. That comes from the first law of thermodynamics, that heat is neither created, or energy, sorry, is neither created nor destroyed, conservation of energy. So we can just kind of substitute that in. We get that the entropy of the surroundings, change in entropy of the surroundings, is the negative heat of the reaction divided by the temperature. We can then use the definition of enthalpy for at constant temperature, the enthalpy is equal to the heat of the reaction. That's just the definition of enthalpy. That's why we use it in chemistry. And so that tells us that the delta S of the surroundings is equal to the negative delta H of the reaction divided by the temperature. So we can see this idea, there's that negative because, we knew that exothermic, so negative delta H would lead to a positive delta S surroundings because that heat flows out into it. So this is the equation we can always use if we want to calculate delta S of surroundings. Let's do that. What is the change in entropy of the surroundings associated with this reaction at 25 degrees Celsius? So it's the same reaction we looked at in the last video. I have propane combustion, C3H8 plus 5O2 gives me 3CO2 and 4H2O. Here are some handy thermodynamic data. So what is the change in entropy? So similar to what we've seen previously, but now it's of the surroundings. Okay, so this is the same chemical reaction at 25 degrees Celsius, but I'm now doing a change in entropy of the surroundings. So we need to use a different equation in this case. And so whenever we're looking to do it, the delta S of surroundings is going to be equal to the negative delta H of the reaction divided by the temperature. So basically what we're looking at is we're going to relate, we know that the change in entropy of the surroundings is due to heat from the reaction. So we're going to look at what heat comes out of the reaction. Negative just changes the perspective, and divided by temperature is what turns it into an entropy. You kind of see there's that K in the reference S values, whereas enthalpy is just energy per mole. So we want energy per mole per temperature. So throw temperature in there. Okay, so what we really then kind of need to do is get this thing first. So we need to get delta H of reaction. And so we can calculate delta H of reaction using reference data. I'm going to do that on a separate sheet of paper here. But we know, again, that delta H for the reaction is going to be, it's always a sum over products. Delta HF, and it's slightly different reference, kind of the name we call for the reference information between entropy and enthalpy. But functionally, we use them in the exact same way. Just these are delta H's that correspond to a reaction, whereas the entropy values are absolute. Functionally, just using them, you can kind of, they work in the exact same way. Okay. So delta H of reaction is going to be based on our chemical equations. So we're going to start with products. So it'd be 3 times the delta HF of my CO2 plus 4 times the delta HF of my H2O minus the reactants, sorry. So that's going to be delta HF of C3H8 plus 5 delta HF of O2. And I guess these all should be, everything technically is happening at 1 bar. So those knots on there. And so, this would be kind of the generic equation, just taking this chemical equation and filling in explicitly what all the products, what the coefficients are, and all of the reactions. Then I can go ahead and plug in some actual values. So that would be 3 times delta HF of CO2 is negative 393.5 kilojoules per mole, plus 4 times negative H2O would be negative 241.8 kilojoules per mole. And then we subtract the C3H8 is negative 103.8 kilojoules per mole, plus 5 times O2, which is 0. It's an element. All elements are defined as having an enthalpy of formation of 0. So then it just becomes a process of doing this arithmetic. I would recommend being very careful. One of the things you want to note, there's a negative sign in front of these parentheses. So whenever you're doing these types of calculations, delta S of reaction, delta H of reaction, and there's another one, see for this other reference, it's very common to forget that this negative sign applies to both components of inside this parentheses. So right here and right here. Both of those do line up. So we do want to be careful and mindful. This is a pretty common mistake when doing the arithmetic. There's a 0 there, so you'd get away with it here. But as a result, we would get that delta H is equal to negative 2043.9 kilojoules per mole. This is burning propane, so it's quite exothermic, which is what we expect. This is fire, so we would expect that to be negative. So that's good. So what we can do is take this value and plug it in right back into that delta H that we wanted. So this is going to be used for delta S of surroundings. We also did figure out delta H of the reaction, so we kind of got that for free. That's a part of it here. We can go ahead and plug it in into here. Delta S of surroundings is going to be equal to negative of the negative 2043.9 kilojoules per mole divided by T. And for T, we always want to use a Kelvin temperature. So it's at 25 degrees Celsius. We always want to use our Kelvin temperature. So 298 K. And so if we put that together, we would get overall 686 kilojoules per mole Kelvin. And that per mole Kelvin, or that energy per Kelvin, that's our standard entropy unit. So we want to, that's a good, I'll leave like that. You'll note this is kilojoules per mole. A lot of times we see joules per mole. It's fine. If you're just getting an answer, this is still an entropy unit. And so we can still certainly use that. I think there should be a 6.86, not 686. Hold on, losing myself now. But so yeah, the kilojoules per mole is fine. And so you can just leave that as it is per mole Kelvin, just important that's there. A lot of times if you're doing other things, we'll convert to joules, but we can leave it as kilojoules if we're only looking for the entropy. And so if we're looking for entropy of the surroundings, we just need to calculate delta H of reaction, which we use the exact same tables. That's why there's all the columns in the table, and you can use them as you need. One of the things with entropy is we always want to check, does the sign make sense? Because we can predict the sign for changes in entropy whenever we're looking at it. And we got a positive value. We got that for this reaction, the delta S of the surroundings is positive. The surroundings are becoming more disordered. That is consistent with this being an exothermic reaction, right? This is a flame, you're burning propane. The air around the flame gets hotter. The flame is where the actual chemical reaction is occurring. That's all that heat is coming out. Your surroundings are getting hotter, and therefore those molecules are moving more. There is more inherent disorder. So exothermic reactions, the delta S of surroundings should always be positive. Only one more video. See if we can find any more participation in that one. See you in the last video.